funziona? Non funziona più. Ah, ecco adesso. Bene, salve a tutti. Allora, insomma, vedo una partecipazione ampia e so anche, diciamo, che ci sono colleghi che non sono del nostro dipartimento. Io vi ringrazio per essere intervenuti, ringrazio il professor Ignazio Sirac per, diciamo, la disponibilità che ha dato per questa dodicesima edizione delle lezioni appunto che facciamo qui in dipartimento. Questa iniziativa particolarmente importante e l'argomento della quantum information è particolarmente rilevante in questo momento perché direi si innesta in un processo e uno sviluppo che stiamo come comunità di fisici di Napoli, come dipartimento cercando di portare avanti sicuramente da un anno, ma che insomma ci prenderà per un po', che è quello sviluppo della quantum information sia dal punto di vista hardware che dal punto di vista, diciamo, software, cioè dell'utilizzo poi della macchina che andiamo a costruire. Di questo fa parte di un progetto molto grande che vede grossi finanziamenti del PNRR. Addentellati, cioè qui si intende costruire una macchina, in realtà una macchina piccolina già c'è, ma si intende costruire una macchina che sia competitiva, che sia tra le più competitive in Italia e poi immaginare di avere il software per utilizzarla e gli argomenti, cioè, diciamo, i progetti, i scientific cases che devono essere affrontati utilizzando una macchina quantistica. Questa è un po' l'idea. Ed è l'idea che stiamo portando avanti, abbiamo portato avanti anche come progetto di dipartimento di eccellenza, anche se, diciamo, non avevamo molte chance per vincere quella opportunità. Ciononostante però rimane l'idea di sviluppare molto questo settore, cosa che come dipartimento stiamo facendo. Quindi in questo momento sono particolarmente lieto che si parli proprio di questo argomento, perché questo è uno degli argomenti, se non l'argomento dipartimento, almeno nei prossimi anni. Quindi grazie per l'organizzazione, per aver scelto il tema e sono sicuro che sarà sicuramente un'occasione importante e sarà un'occasione importante che ricorderemo anche nel futuro perché, ripeto, fa parte di un progetto più grande. Quindi, grazie per essere intervenuti.
A nome del comitato organizzatore della Majorana Lectures, benvenuti. Benvenuti. A nome del comitato organizzatore della Majorana Lectures, benvenuti a tutti i presenti. Vorrei solo ricordare che questa serie di lezioni nel 2020, quando cominciò la pandemia, fu l'ultimo evento in presenza che si tenne qui prima del lockdown e 2 anni fa, quando l'emergenza nazionale non era ancora finita, fu il primo ciclo di lezioni che si tenne in Italia quando stavamo per uscire dalla fase acuta della pandemia, per cui è molto radicata la direzione del Dipartimento della sezione NFN, la direzione di questo ciclo di lezioni. Qui diamo il benvenuto al professor Sirac e a lui, immaginare.
Thank you very much. So it's my great pleasure to be here and to give this short lecture about quantum antibody systems, quantum information, and quantum computation. And so before I start, I want to give a motivation and introduction to the subject. And so it turns out that quantum information now is relatively known nowadays in the sense that people have been trying during the last years to build quantum computers and quantum communication systems, and so there is a big hopes that with this new kind of computers then we will be able to solve problems that with supercomputers we are not able to solve so far. So that's an aspect of quantum information which I think that is very relevant. And I think that is also very relevant for the scientific community. In fact, I mean, my personal view to that is that most of the applications of quantum computation, at least in the next few years, or in the next 10 years or so, will come from scientific research. So they will help in scientific research. Not so much the industry, because I think that they are not advanced enough to do that. However, in scientific research, I think that there is a chance. In particular, in problems that appear in physics, in condensed matter physics, in high energy physics, in condensed matter physics, in quantum optics. And those are systems that are described by the laws of quantum physics and present relevant parts of phenomena that are surrounding us and that we don't understand yet. And the hope is that with quantum computers, then we'll have a system with which we will be able to solve some of these problems, or at least we will have the opportunity or experiment with them and then maybe develop a better understanding or better theories for all that. That's one of the hope and probably one of the, if not the most important application for quantum computation in the next few years. But I want to go a little bit beyond that, because quantum information is not only about quantum computation, it's not only about building quantum computers and running quantum computers. I think that is much more than that. There is a theory behind that, a theory of quantum information. And this theory of quantum information, it turns out that it has been made connections. It's coming from computer science, basically, but it has made many connections now to quantum physics in different setups. So it started making, at the beginning, connections to foundations of quantum mechanics, where people started just doing experiments to try to see if the local realistic theories, are the ones that describe nature, or quantum physics, that is a non-local realistic theory, would describe. There were experiments, and as you know, when the Nobel Prize was given to those experiments, the pioneer experiment that happened at that time, this was a good connection with physics. And then after people realized that quantum physics has something very special about our world, then they started to think about if quantum physics can also help us in information. So just let me give you an example to motivate that. So imagine that they have a qubit. I will define it later on, but a qubit is like a two-level system, a quantum two-level system, and we know that in quantum physics, apart from having the two possibilities of a state, apart from the possibility of having a state that we can call 0 and the state 1, this would be two distinctions of state, we can have superpositions. And these superpositions of states are determined by some complex coefficients, so we will write alpha 0 plus beta 1 as the state of our system, and these alphas are complex numbers. And the complex number can have an infinite number of digits. So one could think that we can take a qubit and then encode in a single qubit a lot of information, because we can just choose these coefficients alpha beta that contain a lot of information. And so people in the 70s were trying to figure out if it is true. If we can encode an infinite number of information on a single two-level system, and it turns out that it's true because of what I say. However, they show that this information cannot be extracted, and the only information that you can extract from a qubit is a single bit of information. So this made a connection between quantum theory and information theory, and people started thinking a little bit about, so what was what are other possibilities beyond, storing and retrieving information, and there's where processing information was led to quantum computation. But nevertheless, in order to develop this theory for quantum information, quantum computation, they had developed some of the theory, which is what we call in the jargon entanglement theory. And so people started talking about entanglement and showed that whenever you have an entanglement, which I will explain what it is, then you have more power in quantum information than with classical information. So develop a theory of entanglement. And what I wanted to say is that this theory of entanglement, during the last 15 years or 20 years, has made also connection with other areas of physics. Started with condensed matter physics, which people realized that if you have a condensed matter physics system, and if it has very little entanglement, then actually they can describe it very efficiently with a classical computer. However, when it has a lot of entanglement, then I will not be able to describe it with a classical computer, and that's when I need a quantum computer. So the theory made the connection first with condensed matter physics, then started connection with high energy physics, in the sense that for lattice gauge theories, then you can also have the same kind of arguments, that if you have a lattice gauge theory, which is described by some gauge group and whatever, then you want to now to solve it with classical device, you better have little entanglement in your system because otherwise it will be difficult. So this was one of the connections that related the theory and some of the methods that were developing in quantum information to other areas of physics. Now in the last 10 years or so, it has been also connected to quantum gravity in the sense of the information paradox and black holes, and so people are now using the tools that were developing quantum information to describe some of the black holes evaporations and quantum properties of black holes and so on. It's very popular in some places. And again, so the theory that is behind, I mean, independent of quantum computation, is the one that has made connections. So now it's very nice for people like me who have been educated in quantum information that I can talk to people in high energy, condensed matter physics, and even in string theory, and because we use the same language. And so what I want to do in this lecture is not only to talk about quantum computation, but I want to talk about this language and make the connections to these other fields. Now, let me go back to the quantum computation part. And so I was mentioning that, so I want to tell a little bit about history, so how this connection between quantum many-body physics and quantum computing started. And so at the late 70s, when people were developing these first steps of the theory of quantum information in order to see whether with qubits we can store and retrieve more information or how, then there was several revolutions were occurring. So on the one hand, people had discovered years ago the transistors and they're making computers smaller, smaller, smaller and faster, faster, faster. On the other hand, in quantum field theory, people started doing renormalization, lattice theories, and realizing that if you have a computer, then you could solve problems in quantum chromodynamics or in quantum electrodynamics, and so on. And so at that time, some of the people were concerned that if we take now transistors and make them smaller and smaller and smaller and smaller, because if we make them smaller, then they have more capacity, because they have more memory, but also they are faster, because the electrons have to go a shorter distance. By trying to make computers faster and faster, faster, therefore smaller, 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 at some point we will reach quantum physics. At some point you will have to have transistors that have few atoms, and the description that I had at that time for transistors were completely classical, so you will be confronted with quantum physics, and in quantum physics, everything fulfills some laws. So for example, if we describe quantum physics with a standard formalism, the dynamics of the system is described by some unitary operator or some Schrodinger equation if you want, and these equations are reversible. Whereas transistors and computation work irreversibly, so you erase something, you get rid of information that's irreversible. And so they were concerned about the fact that while you're trying to make things smaller, you will confront quantum physics and you will have to get around it and try to avoid all the quantum mechanical problems or properties in such a way that your computer will work. And so they started thinking about reversible classical computation. So can we make a computation, build classical computers in which we don't have to race, because then it could be reversible, and then there is a hope that quantum physics could help with that. And at the time, there was a conference in some island in which people coming from computational physics or quantum physics and so on were meeting in order to discuss, some scientists to discuss about the problem of computers getting too small that they have to avoid quantum physics. And at that point, Richard Feynman was invited to that conference, and so he gave a talk that became very famous, not at that time, but later on, because he didn't talk about that problem. So what he said is not, quantum physics is not negative news. The fact that we can reach quantum physics is our positive news. Because he knew about lattice theories and the papers by Susskind and Kogut and all these people, then they say, well, these problems that you have when you take quantum chromodynamics, you discretize it, and you want to solve this problem, predict some physical properties of the system, actually is enormous. Everything will grow exponentially. So the computational resources in a classical computer would grow exponentially with the volume that you want to deal with, and then it makes this computations very, very difficult. However, if you would have a computer that obeys the rules of quantum physics, then you could solve it much more efficiently. And so this was the first time, I think, when, at least on writing, because this is written in a paper, that somebody realized that quantum many body physics, like they appear in lattice gauge theory, but also in condensed matter physics, in chemistry, in many systems, are very difficult to deal with classical computers, unless, I mean, we can do perturbation theory, unless some regimes, but in general they are very difficult. Whereas if you have a quantum system, you have a quantum computer, then some of these problems could be solved very efficiently. And so, I mean, speaking maybe a little bit, exaggerating a little bit, there are problems that we probably will not be able to ever solve with a classical computer, one in physics and in exact simulations. However, you had a quantum computer, then we will be able to solve them, just because the resources only grow linearly with the volume and not exponentially with the volume. So what I want to do in this lecture is then twofold. So first is to make a connection with quantum many-body physics. I will talk about quantum many-body physics, and I will talk about quantum information theory, just connecting the two in a single language, giving some examples maybe from condensed matter physics and from lattice gauge theories. And then I will talk about entanglement, I will talk about area laws, I will talk efficient descriptions, I will talk about quantum computation, I will talk about complexity theory. So, I mean, the things that I'm saying with words, one can mathematically rigorously define them, so what is difficult, what is simple, and so on. So I will try to do that. Then my second lecture will be about now some particular classical methods to describe many-body physics without quantum computer that are rooted into quantum information theory. So those are some of these techniques that I mentioned that were developed many years ago that have been exported now to describe many-body physics. And in particular, something which is called tensor networks, and in which I've been in the group, and many of the people in the work have been very much involved in the last 20 years, and that is able also to address some problems, not only from the numerical point of view, but also more from the conceptual point of view, like you want some topological phases of matter, SPT phase, protected phases, and so on. So this has been described in terms of these tensor networks, apart from some numerical algorithms. So this is the second part. So it's like quantum information, but using classical devices to describe many-body physics. And the third lecture is about quantum computation, and so how quantum computers can address the problems that I'm going to describe on the first day. Okay, so that's the plan, and so I'll start very, very easy. So I apologize because I guess that many of you know these things that I'm going to say at the beginning very, very well, but I wanted to have a kind of self-contained lecture, and so that's why I started very simple. So I start with the setup. So this is the first lecture. Can you see from the back if I write like that? If you cannot see, so I tend to write smaller and smaller and smaller, so just let me know, just raise your hand and then I'll try to come back. So this is quantum many-body physics and quantum information. And so I start talking about the setup that I'm going to consider. And so typically, when we want to describe many-body physics in the context that I'm going to do, context of quantum information, we work in lattices. So this means that if we have a solid state that we want to describe, then there's a typical lattice there because the atoms are, just in a periodic structure, and then the electrons move there or the spins are there, so there is a lattice structure. You don't have a lattice like in free space, or if you're really high energy physics, then you can discretize space. We will also discretize them later on, and so you can set things on a lattice. If I have time, I will also talk about the continuum limit because it's possible to go to the continuum in some of the things that I will talk about, but most of the time I will talk about the lattice. And you can consider an arbitrary lattice, but here I will consider regular lattices. So like, for example, this would be like a square lattice in 2 dimensions, but we could work also in 1 spatial dimensions, or 2 spatial dimensions, or 3 spatial dimensions. And for people in high energy physics, here I'm going to talk all the time about spatial dimensions. Okay, there is no time dimension, so here we will work with the Hamiltonian formalism. Somewhere there is a space, and that's what is here, and then time will be a different variable which we generated by Hamiltonian. But this is space. So now once we have a lattice, then we put Hilbert spaces, or if you want some particles, at the edges or the vertices of these lattices. So you can think that there is a spin in each of these lattices, for example, that's one possibility. So in which case we will assign some Hilbert space here, which will be finite. So for example, this could be C2, we have qubits. So this would be that we have a spin 1/2 we want at each lattice side, or we call them qubits, state, system that can take the values state 0 or 1, or could have higher dimensions. That's one possibility. Another possibility, I'm not going to write it, but I'm going to say is you don't need to have spins. You can have fermions, for example, in which you will have a lattice. Then you will not build the whole Hilbert space as a tensor product, because you have to be careful where you are with fermions. But still, what we can do is that we can assign now operators to each of the lattices. For example, creation and annihilation operators corresponding even to some internal dynamics. You can have some spin, it could be at some lattices, and they could have some spin. And then we can describe the motion of some fermions with spins on the lattice. Now, you're talking about lattice gauge theories, then you have to add a little bit more, because apart from fermions, you can have bosonic gauge fields. And in that case, in your lattice, you will also use your vertices, your edges. And in the edges, you can put some other Hilbert space. These are bosonic Hilbert space, typically an infinite dimensional Hilbert space. And this could correspond, for example, if you're describing QED, in which you can have electrons or positrons that are moving on the lattice, maybe with some staggered configuration, and every time that an electron hops from one side to another one, the gauge field changes. For example, the electric field changes by 1, and so on. And so everything can be described in lattices. So that's the setup. We have a lattice which can describe, as I'm saying, some spins, or some electrons and bosons, and so on. The second thing that we have to define, so in the case of spins, so most of the time we'll talk about spins to make it simpler. And in the case of spins, of course, we'll have that the whole Hilbert space would be just the tensor product of these Hilbert spaces of each lattice size. So lattice size, so each of the vertices can be described in terms of some vector, right? We tell you just the coordinates. And so for each lattice size, we have, say there are lattice size, then we'll have some Hilbert space for this lattice size, and the whole state will be described by this tensor product. So the next thing that we are going to describe are the states of the physical states will live in this Hilbert space. So if I have a pure state, then I'll have some state which would be in an element of this Hilbert space. And we see right away why we have this exponential explosion of resources when we deal with these systems. So imagine that I have now, the simplest case, n qubits, or n spin 1/2 system on the vertices of some two-dimensional lattices. And then you just take one state in this Hilbert space and write it in some basis, what we call computational basis. So I can build a basis just by taking here this Hilbert space on a single side and define a basis. So write it like that. It is spanned by the states 0 and 1. So what I mean is that if I have a single qubit, then I can write the state as a linear superpositions of 0 and 1. That's what I mentioned before. And this is at some lattice size. And if I have the whole Hilbert space, then I can have states that would be something like n1, n2, and so on. And with this n can be 0, 0, 1, for example, I can have the state 0, 0, 0, 0, 0, 0, which in terms of spin would be all spins down. I can have a state 0, 0, 0, 0, 0, 1, all spins down and 1 up, and so on. And the general state in this Hilbert space, written in this basis, would be a linear superposition with complex coefficients. So now you see what I was telling you before. Imagine that I have some state in this lattice that I have prepared, or that nature has prepared, and I want to communicate what is the state. What is the state? So what I'll have to tell you is with our these coefficients, because these coefficients completely characterize the space. And since the indices here are running from 0 to 1, even if you have the simple system qubits, then you see that there are 2 to the n coefficients. Or in other words, the dimension of your Hilbert space, because we have a tensor product, is equal to 2 to the n in this case. So the number of coefficients, the information that I will have to tell you in order to describe the state grows exponentially with the number of lattices. And if I have something like 30 or 40 or 50 lattices, there is no way that I can even store in a computer these numbers. And not only that, so imagine that I want to make a prediction with these numbers. I want to compute something, or I want even to compute these numbers in order to tell you. For each of the numbers, probably I will have to do one operation. So the number of operations that I will have to do to answer any question that you ask me will be proportional to the number of coefficients. And since I have an exponential number of coefficients, the computational time will be also exponential. So there is a very specific situation that we have here, is that whenever we have a quantum state of n qubits, and I want to do anything with that on a classical computer or on a piece of paper, I need exponential resources. I need an exponential memory, a memory that grows exponentially with the size of my system in order to store these coefficients, and in order to compute these coefficients, to make any prediction, I need an exponential time. And that's this bottleneck that Feynman was talking and realized, which is quite obvious, that as soon as we'll have something like 20 or 30 qubits, there will be no way that we can solve this problem exactly. So maybe you have some symmetries in your problem, and instead of 20, you can go up to 40, right? But if you have 1,000, I mean, the Hilbert space dimension, 2 to the, or 300, 2 to the 300 is equal to 10 to the 18, so it's the number of the barriers that we have in the universe, and this gets out of control. And now this also tells us what I told you before, that if I want to make a prediction about some system, what about instead of writing down these coefficients and doing the computation with these coefficients, why don't I take a quantum system, qubits, I prepare my qubits on this state, and then measure my qubits, and then I will be able to answer this question. And this was what Feynman was saying. So if I'm able to take a set of qubits in a way that I can prepare the state of which I'm talking about, then I will be able to do things without an exponential growth of memory. I will need only n qubits to represent n qubits, not an exponential number. And I will need only the time that will be short as compared to this exponential time. So that's what's behind all that. Anyway, so the next thing is that, so what do we want to do with these states? So typically in physics, once we have some state, then we want to predict some physical properties. So this is why we talk about observables. And that's why we can associate to each of the Hilbert space a set of remission operators acting on this Hilbert space. This is what we would call local observables. And now, that's what we learn in quantum physics, that we can consider now all possible observables in the Hilbert space, and this will be basically a resetter of linear and remission operators acting on this Hilbert space. But typically in physics, we don't want to have all possible observables. We care about few of them, which are physically relevant. So for example, the local observable. So I would like to know, so what is the spin here, the expectation value of some spin operator, like the magnetization here. And that's why typically we define something that are local observables. I could say my observable n is an observable with here. N is something that, strictly speaking, acts trivially. We write it is the identity operator everywhere except at the n size, where I have some operator, we write it like that, and the rest are identity. So this mathematical formula, if you're not familiar with that, what it means is that I have an observable just at this particular point. This is what we call a local observable. Now we can have pairs of observables, and this derives, for example, to correlation functions. So we can have, for example, O and M, and this would be something that is everywhere the identity, then maybe some operator at sign N, and some other operator at sign M. And these are some other operators. In the same way, you can define 3-body operators, 4-body operators, 5-body operators, and the most general would be n-body operators, and all of them themselves, they form a linear space, a Hilbert space, and the set of all operators are in Hilbert space. But what I'm saying is that, fortunately, in physics, we are interested only in few of them which are very peculiar, because they act only on some small regions or in pair of regions, and so on. And so, so typically, what we're interested in physics is predictions about what is the expectation value of some of these observables. So in other words, if I have some material which is made of fermions or spins, and I have certain states that has been produced by nature or by whoever, at the end I want to make predictions. I want to know what is the magnetization of this spin. The way that we do it in quantum physics is that if we are able to have the state or to produce this state, then we will compute the expectation value with this state. So we'll compute something like, we'll define like that, right, with this Ranket kind of language. And so this means that if I would prepare the state, I measure this observable corresponding to this operator O. And I measure it again. I repeat it, the experiment many times. And at the end, I take the average value. Then in the limit in which I do an infinite number of measurements, this corresponds to this quantity that I'm calculating here. So this tells you what are the possible expectation values of the observables that are acting on single sites. You can measure correlations. So for example, you can compute, following the language, something like ON, right? ON, AN, DM. So this would be that we are looking at some observable at site M and some other observable at site M. And now we are measuring two of them, multiplying them, measuring, multiplying the result, measuring, multiplying the result, and at the end calculate the average value. And so this will be given by the same formula where we do sandwich in the state operators. And sometimes I will talk about what we call connected correlation functions, which is that we compute just the expectation value of the product and we subtract. These are what we call connected correlation functions, and this will come up later on. Okay, so now, so for the moment here, there is no prescription of, we have a clear prescription of how to define these observables. I mean, depending on the system, it could be spin along the z direction, it could be the number of fermions at some point, it could be anything like that. But we don't have prescriptions of how to compute the states. And in quantum physics, we also learned that in order to make predictions about how the state changes, then we need to give a Hamiltonian. So among the all possible operators or observable we have, there is a specific one which is very important that describes the interactions in our system. It describes how the electrons move, how the spins interact, or how the matter interacts with the gauge fields. And so in the Hamiltonian formulation, which is the one that I'm using here, and at the end, this means that you will have to give me either based on first principle from the standard model, you have to derive it, or in some solid state physics, because phenomenologically you find out so what is how the systems are interacting, some Hamiltonian. And I mean, we call it H, don't confuse it with Hilbert spaces. And so this tells us about so how our system will evolve, but also about the equilibrium properties of our system. So the Hamiltonian gives two kind of information. So one of them allows us to predict, given some initial state, so how it will evolve in time. So we know by Schrödinger equation tells you that if I start by some state, psi 0, then after some time I will have some state which can be calculated as e to the minus I ht. So you have to take this operator, take the exponential and so on, and then when you compute it, and this is the state after some time. And so this gives rise to what we call dynamical problems, in which you're going some initial state, you're going to the interactions, and you want to know what are the physical properties of this system after a certain time. Then the way that you will do it is, if you know the Hamiltonian, this you have to know, otherwise you cannot do anything. If you know that, then you put here the initial state, you will do this operation, which is equivalent to solving the Schrödinger equation. You will compute the state after some time, and once you have the state, you use this prescription to compute the expectation values, and then you will be able to make predictions about the physical properties of your system. Okay, so that's dynamics. So the Hamiltonian also tell us about equilibrium properties. So the principles of statistical mechanics tell us that if we have something which is called thermal equilibrium, which is a definition, tells that two things. So first of all, is that our state, the state that describes our system, is not pure, will not be described like that. And so I hope that you know what the difference between pure and mixed state is. But it will tell us that this is a mixed state. And so mixed states are described not by elements of Hilbert space, but are themselves operators of Hilbert space. And these operators of Hilbert space have some properties. They have to be self-adjoint, they have to be trace class, trace one, and so on. So they have to be positive operators. So it means that your state now will be given by something which is called a density operator. And just maybe to write it here, that the expectation values now of observables, you have density operators, are computed not using the sandwich, but using trace property. And so if you are not familiar with density operators, I know that if there are students here, maybe you're not so familiar, then it's not so important, just consider pure state. But anyway, so statistical mechanics will tell us that we have a mixture, now, a mixture, and this mixture can be written in terms of the Hamiltonian and the temperature, where beta here is a parameter, is 1 over T, and I'm using units in which h bar and the Boltzmann factor is equal to 1. And dc is just the trace of e to the minus beta h, which is also called partition functions. Okay, so again, so if I have a system and I let it equilibrate, what we call it equilibrate, it has to be defined, but then I don't have to do compute evolution. Then I go to a book of statistical mechanics and tells me that if I want to make predictions of what happens in equilibrium, what I will have to do is to take, again, my Hamiltonian, put here what is the temperature that I have in my system. I'll have to measure, and if I know the temperature and I know the Hamiltonian, I know the state, which is mixed, and once I know the state, I can make predictions, like I told you before, just using this formula. I can say, what will happen if I measure in that state an observable many times and then I average, and I can predict it with this formula. So these are problems which are called in equilibrium, thermal equilibrium. And this is called also the keep state. Now there is some particular case which will be very, very important, and here is a case in which we have zero temperature. So what happens if we lower the temperature and then we go to zero temperature? Then you can take the limit here where this t goes to zero, namely where beta goes to infinite, and you can realize that the state that appears here is nothing else but a projector into the ground state of H. Okay, so you're at zero temperature, then what the state that you will have will be, let's say, if it's unique, the ground state of this Hamiltonian, so the lowest energy eigenstate of this operator, that's the ground state. You have the generosity, then you have, there are many of these ground states, you'll have a mixture of those states. This means that right here, for t equals 0, then we have that the state that I have, if it's unique, will be psi 0, which is called the ground state energy, and is the lowest eigenvalue. This is an eigenvalue equation for H, and it's the lowest eigenvalue, and this will be the eigenstate. If there is degeneracy, then you will have many of those, and you will have a mixture of those. Okay, so I know that you know this very well, but nevertheless, I wanted to just to be on the same page to have these definitions. Okay, so let me give now some examples, and with these examples I will introduce a limit of notation for most of the examples that I will have here. So I already talked about qubits. That would be the simplest case in which we just have spin 1/2 the vertices, and we can call the state spin down 0, spin up 1, have superpositions, we can write states like that. Now, we have observables. The observables for a qubit, these are described in terms of these operators that act on single sides. and these operators that act on single sides, are expressed in terms of what are called Pauli matrices, and these Pauli matrices are called sigma x, sigma y, and sigma c. And these Pauli matrices can be written like that, in terms of this breadth, get and wrap notation, like that. And sigma c is minus I times sigma x times sigma y. You can just multiply them out with the rules of this. Whenever we put two brass and ket, and there is like the inner product and so on with orthogonality conditions. And you also have the identity operators. So these are operators that are very familiar for most of you. The period when you study angular momentum and things like that. These are representations you write in terms of 2x2 matrices, or representations of SE2, or are generators of SE2, and so on. So then, right, so now what I will do is that I write some example Hamiltonians that you can have, some many body problems that are sometimes difficult to solve. And now, so examples. So one example could be a problem in which, again, so if I want to specify my problem, I have to specify the lattice. So I can say, for example, I have a two-dimensional lattice, square lattice. It could be a rectangular lattice, it could be something else. And now I can write here, I have to give you the Hamiltonian. So my Hamiltonian could be, for example, this Hamiltonian in one dimension, it's right here 1D. Sum sigma c and sigma c m plus 1 plus h sum of sigma x n. This is n. This is n from equal to 1 to n, and this n plus 1 is modulo n, such a way that you have periodic boundary conditions. So that's what is called an Ising model in a transverse field in one dimension, and you see that they appear just the operations that I told you. So this, for n equal 1, this is the sigma c acting on the first qubit, and the sigma c acting on the second qubit. Then you sum all of them, you have a transverse field, and that's the Hamiltonian. Another Hamiltonian could be, for example, in 2D, h equal to sum, now we sigma x n, sigma x n, plus sigma y n, sigma y n, plus sigma c n, sigma c n, n. This is also a name, it's called the Heisenberg Hamiltonian. And so what it takes, and this means that the sum is restricted to nearest neighbors. So this takes here one of the vertices of the lattices. It takes the one that is connected by one of the vertices, takes these two, takes sigma x, then sigma y, sigma c, sigma c, then takes another one, then takes another one, then takes another one, and so on. And this builds the Hamiltonian with that. It's a Heisenberg Hamiltonian. This could be in 2D or 3D or 1D. These are some of them. Now you can combine them, so you could have now different coefficients here, and so on. So these are typical problems that appear in spin physics. Now we can have Hamiltonians, now including fermions. I'll give you an example. H equal minus, call it tau, sum, m, a, variant, and sigma, a, and sigma, and sum of sigma plus u divided by 2, sum, and n, and a dagger n up, and dagger n up, and dagger n down, a n down. So you see, now I used not the spin, but the fermionic operators that I defined before for each of the lattice size. Now they have the index corresponding to the position, so to the coordinates. They have another index which represents here the spin, so the sum in sigma goes from spin up, spin down. And so this describes fermions hopping from one side to the near side, so like electrons would move on a lattice without changing the spin. So if they're spin up, then they move with the spin up. And the second one represents an interaction. Whenever there are two spins on a single side, one spin up, one spin down, then this term is acting, so it gives some energy. And that's what is called the Hubbard model. And so the Hubbard model is a typical model, which is very difficult to solve with any problem whenever this U is positive. This is pointers to the repulsive Hubbard model in 2 dimensions. And as you know, one of the questions that people have is whether this model describes high-density superconductivity. The physics of high-density superconductivity, which is a difficult problem to solve with classical computers because we have this exponential growth of the resources. Now, so I will not insist much on that, but now you can have, on top of that, the gauge fields here, so bosonic fields, so now bosons in the middle. And so you could have a model in which every time that you annihilate a fermion at some size and create it nearby, there is a bosonic field, some unitary bosonic field, which like e to the I phi, where phi is the bosonic operator, and this would represent that every time that you hop from here to here, something is happening to the bosonic field. And on top of that, you can have the mass of the fermions, so you have a term which will be sum of A daga n A n. And on top of that, you have the electric and the magnetic energy. So you have some bosonic field, some sum of E squared n, where E is the electric field at each side, and the magnetic field is a plaquette term. So it will be a term that includes in 2 spatial dimensions, these 4 gauge fields, and that has certain symmetries, and these are the gauge symmetries and so on. But what I want to say is not to go to specific examples and talk about physics with these examples. What I want to say is that all these problems that appear in condensed matter physics and lattice gauge theory that can be embedded in lattices, at the end are described in terms of some Hamiltonian, some Hilbert spaces, and the goal in all these systems is basically to find the states given by the dynamics or the thermal equilibrium and making predictions on the systems. Okay, so is there any question at this point?
I have a silly question. Given your right to use the notation you prefer, is there a reason for which your sigma c that you use in Hamiltonian is not the diagonal one as we have done for...
No, it's diagonal, so you multiply sigma x. Oh, I'm sorry, this is sigma c. Oh, I'm sorry, this is sigma c.
Okay.
I'm sorry, yeah, so this will be sigma sigma x. I'm sorry, yeah, you're right. No, this is, no.
Reason for which you wanted that...
No, sorry. No, this is that's the sigma c, standard. No, I confused. I mean, I don't remember, I mean, this is, if you write it down, this will be 0, I minus I, 0, and I don't remember where is the plus or the minus, and there in quantum information you use a different sign than in quantum optics, and so I don't want to get into the...
I thought it was a ruse.
No, there's nothing mysterious, a mistake.
Yeah. Okay, fine.
Okay. Any other question? Okay, so then I continue. And so now I'm going to change a little bit. So I've been talking about these kind of many-body problems, so the problems that we would like to solve in physics. And now I'm going to introduce a little bit of technology of quantum information. So I'm going to talk about something that has apparently nothing to do with that, and then I will put them together. So I'm going to talk about entanglement theory. Entanglement and correlations. Okay, so now let me consider just a very simple system in which we have only 2 lattice sides. Okay, so this is what we call bipartite systems, and also I'm going to consider pure states for the moment. Okay, so pure state, which what this means is that I'm going to talk about the elements of the Hilbert space, and I'm going to have only bipartite systems. So bipartite, and bipartite means that I have just 2 lattice sides And in fact, I'm going to make it much simpler, so you're going to have qubits at the moment, so 2 qubits. Then we can write a state as some C00, 00, plus up to C1111. That's the notation that I wrote before. So any state of 2 qubits can be written in the computational basis in terms of the 0 1s with 4 coefficients, which is the dimension of the Hilbert space. Now we can have 2 kinds of states. States which are called product states. That's the definition. So that state psi that can be written as some phi on the first system, and we call it 1, and some state eta on the second system. So these are states in which you can imagine you have these 2 qubits. I can take the first and I can assign the state to the first one, psi, and I can take the second one, I can assign the state to the second one. For example, the state 0, 0. I give you the state 0, 0, I have the first qubit spin down and the second qubit spin down, and I can assign very specifically what is the state to the first qubit independent of the second qubit. These are both. Another state could be the state, for example, plus plus. Product state, where plus is defined as 1 divided square root of 2 of 0 plus 1. Okay, so if I write it down, it will be something like 1 over 2. No, it's plus 0, 1, plus 1, 0, plus 1, 1. So, as you see, if I would write my state like that, it may not be immediately obvious that it's a product state. However, you can operate here, take common factors and so on, and then you see that you can write indeed as some state phi plus here and state plus here. And so, for this state here, I could assign a state to the first qubit. It will be a spin pointing in the x direction in the language of spins, and the other one is pointing in the x direction. And so I can assign to them independent states. So, these are the product states by definition, and an entangled state is a state which is not a product, so cannot be written as a product state. Entanglement is the same as no product, by definition. For example, the state it's very easy to convince yourself that if you try to write it as, for example, alpha 0 plus beta 1 times, sometimes I write it simple, sometimes I don't write it, but anyway, and 0 plus delta 1, and you multiply them out, and then you impose that alpha gamma is equal to 1 to the square root of 2, that this doesn't have solutions. So this means that this state cannot be written like that, and therefore it's not a product state. So you cannot assign a state to the first system and a state to the second system. You have to assign a state to both systems. And the first thing that you notice here is that these states possess correlations. So whereas the product state, if I measure something on the first system and then I measure something on the second system, the outcome of the second system will not depend on the outcome of the first system. Whereas in the entangled state, it will not be like that. If I measure the first system and I sigma c and obtain spin down, obtain 0, then the second system has to be spin down. It depends on the outcome, and this gives 2 correlations. Or in other words, if I would compute connected correlation functions like I defined before, then for these states will be different from 0, whereas for those states, all of them will be 0. So we say that we have entangled states, and these entangled states are correlated, give rise to correlations. Now, there is a way, I could give you another entangled state. For example, that's another entangled state. You can also show that if you try to write it in this form, it will not be possible to solve these equations. And this also has correlations. And however, so I could make this coefficient smaller and this coefficient bigger, And at the end, I can approach as much as I want the state 0, 0 being entangled. So there should be some notion about how much entanglement I have. So if I'm very close to a product state, the entanglement probably is very useless, whereas if I'm not close to the product state, I have entanglement, and then if entanglement is useful for something, then this state should be used for something. So that's why we define a measure of entanglement, and the measure of entanglement for these qubits is very easy to compute. It's what is called entropy of entanglement. So entropy, entanglement entropy, which given a state psi, so right like that, it assigns some number which gives an idea of how much, how far I am from a product state in some distance measured. And this is, by definition, defined as the von Neumann entropy of the reduced state of A. So I have to define what is the von Neumann entropy. The von Neumann entropy of some density operator minus trace of rho log in base 2 rho. So quantum information, we use base 2 logarithms. And the reduced state rho A is defined as the partial trace to the state of B of psi psi. So I'm saying, if you're not familiar with this density operator, it doesn't matter. I mean, it's not the time to learn it here in this lecture because there are more important things. So just ignore it. There's a formula that tells you how much is entanglement, and then you can compute. And you can compute it for this state, and you will see that this measure of entanglement for this state is equal to 1. And for any product state is 0. And for any other state is between 0 and 1. And actually the physical intuition why this is a good measure of entanglement, you can see it from here. So in this state here, if I measure the second system, but I don't tell you the outcome, then your state is a completely mixed. You don't have any idea about any information about your system. It would be what we say, the density operator, the reduced density operator, would be completely depolarized, or would be the identity operator. So it has no information left. So this means that by neglecting one system, by discarding one system, then we lose all the information. It's completely mixed. So it has a lot of entropy. If we take two systems that are in a product state and we discard one of them, the other one's still in a pure state. So it's not mixed in a pure state. And therefore, by discarding one, we still have all the information there. And that's why this entropy, as you know, measures somehow the information that is in some state, or the mixedness, which is the same. So by measuring the mixedness, then we can know something about the initial state. I'm saying this is not important, just to mention that there is a measure of entanglement. Now, what we could have is, instead of 2 qubits, we could have higher dimensional systems, qubits or higher spins, or we can have bosons, we can have infinite dimensions, or whatever, and we will do the same exercise. We will define product states as the states that can be written as a tensor product. The states that are not are entangled, and we can assign a number to how much entanglement they are. By this entanglement entropy, we will compute the reduced state, the entropy of the reduced state. This will give us a number that we associate to this entanglement. And in the case of a d-dimensional system, so this is between 0 and d, and the states that saturate this value, the ones that have the maximum entangle, are called maximally entangled states. And examples thereof are generalizations of those here that I will use later on. And this is why I just write them down here. So it's big 5. We call them typically 5 plus for some historical reasons, which is 1 divided by root of d. Sum over n equal 1 to d of nn. These are examples of maximally entangled states, meaning that they live in a d-dimensional Hilbert space, 2 qubits we call them, and they have maximum entanglement of those. Right? So that's nothing very special. So it's just a definition, and this definition of entanglement. And if this lecture will be more about foundations, something like that, then I will tell you that these entangled states violate Bell inequality or generalized Bell inequality. So this means that you cannot make a local hidden variable theory out of them, and therefore if you measure something with them and you observe that this cannot be predicted by any local hidden variable theory, then you're demonstrating that nature doesn't follow local hidden variable theories. These are the experiments that Aspect and Clauser and Tyler were doing, and because of that they got the Nobel Prize. But anyway, so want to go on. Now going to multi-partite systems, and this will be important because in the lattice we will have not only two lattices, we will have many of them, and therefore that's why we want to go to multi-partite. And now, in principle, I mean the whole incomplete entanglement theory for multi-partite states that I'm not going to describe here, but I'm going to say some things which will be relevant for the rest of the lecture. So I can now give you some examples of multi-partite states. Imagine that I have n qubits or qubits, and then I write a state which is 0, 0, 0, 0, 0. This state will be a product state, so we can define product states there, which are the ones that can be assigned a state to the first qubit, a state to the second qubit. And entangled states will be the ones that are not like that. And one example thereof would be this one here. And this is called the GHC state, Greenberg-Horn-Zeilinger state, because these are the ones who introduced the state and noticed that for something is interesting, for biology and Bell inequality, but we know also that for quantum sensing, quantum metrology, they're relevant, but they have a proper name. It's an example of entangled state. Another example of entangled state would be this one here. So it's the one that has everything 0 except 1, 1. And we have a linear superposition of all the possible situations in which we have a 1. So this, in condensed metaphysics, we would call it a spin wave. So there is a spin that is completely delocalized with a 0 momentum, and so this is spin wave. In quantum information, we call this a W state. And then would be some other examples like that. Now, yep. Oh, I see. Okay, so I finished with that. So just to mention that now, how does one define entanglement? So is this state more entangled than this one or less? And now that's where this theory of multipartite entanglement takes over, and it's complicated. There are different measures. There is not a single measure. But the one that we will take here, the one that is only relevant for this lecture, is that what we can do is that we have, like in a lattice, we have many of these qubits, like this. And what we can do always to define some kind of entanglement is to divide it into a bipartite state. So we take and disjoint partition of two sides. We take the sides that we call A, the sides that we call B, and then now we have a bipartite system. So we can talk about two systems, and we can talk about the entanglement of these two systems, and we can compute the phenomenon entropy, or the entanglement entropy for these bipartite systems. I will repeat it later on. I think that it's time to stop. But anyway, so once we have that, this is basically most of the things that I wanted to say about quantum information. I can start putting things together.
There is a half an hour break, then the second half of the lecture and a long discussion session. So we might go coffee break and understand the Zoom, and we will leave within half an hour.
like that. Let's say M1 and for M1, 2, or MA and B. So I will have here some 5 MA and B. So this would be all possible configurations 0, 0, 0, 0, 0, 1, corresponding to all the ones in A. These are the ones in B, so you can always just remove terms, call of them an A, call this AB. So we have a bipartite system, right? The ones that are in A, the ones that are in B, put together. And so now we can apply the entanglement to this bipartite system. So we can complete what is the entanglement with respect to this bipartition A and its complement, which I will call EA of psi, which would be just the entropy of the reduced state of A. Okay. And in this way, you see that it will be relevant when we talk about many-body systems, because as I mentioned before, if the states have little entanglement, then we can describe with classical computers. If they have a lot of entanglement, we cannot describe with classical computers, we need quantum computers. And this entanglement will be with this bipartite entanglement. That's why I'm defining it here. Now, this was for pure states. I want to introduce also for mixed states some measures. And there is a whole theory of entanglement for mixed states. I'm not going to talk about here. I just want to introduce the measure that is relevant for what I'm going to tell later on. And that's not a measure of entanglement, it's a measure of quantum correlations or of correlations in general. This is why I call this chapter entanglement and correlations. So now I go to mixed states. And again, now for mixed states, we have now these bipartite systems, and we will have a mixed state corresponding to maybe 2 qubits, A and B. And I'm not going to write it. As mentioned before, you can define measures of entanglement, that this will be relevant for this lecture. You can have a multipartite system. You can have a mixed state. Now, you have many of these particles. For example, you're in thermal equilibrium. I mentioned before that the state is described by a mixed state like that, where there are many particles. And now we want to talk also about entanglement of correlations in that system. And I already said before that whenever you have entanglement, you have correlations. So entanglement and correlations are very much related for pure states. And for mixed states, it's very convenient to measure, to define some measure of kind of entanglement and correlation, which is called mutual information, or quantum mutual information. It's coming from information theory. Quantum mutual information. So if I was giving here how much information there is in a book and how much information is in something, then I will tell you that something which is called the mutual information, which is if I have 2 books, by reading one, how much do I learn about the second one? Okay, so this is how much by looking at the system I learn about the other system. And so there is something similar in this quantum mutual information. And this quantum mutual information, if I have 2 systems, then I define like S, A, B, so A, sorry, I, typically it's written like A, colon B. So that's the mutual information between system A and the system B. Is defined like the entropy of the first system plus the entropy of the second system minus the entropy of the whole system. Okay? So you just take, you have a system, you have 2 systems, you look at the entropy of each of them, and the entropy as a whole, and you just compute that. And it turns out that this quantity here, it's very important because it has an interpretation in terms of information, as I mentioned before, but it also bounds all possible correlations. So you have now any observable in A and any observable in B. And then you compute the correlation functions that I mentioned before, like the trace or rho A or B, minus the OA or B. This is what I call connected correlation function. This is a measure of correlations. Then you take the absolute value of the quantity, and then you take the maximum of all possible observables, maximum with respect to all possible OA and B, normalized in some way, which is with some norm, called here the operator norm, smaller or equal than 1.
So this basically tells you, you take two systems and you look at the observable which will give you the maximum correlation between the systems, properly normalized. That is always smaller or equal than the mutual information. So it upper bounds the best correlation that you have. And maybe for people working in statistical physics, this is not so much used, but in quantum information it's very much used because there are certain states which are used for data hiding. So you have many agents, and then you want to give them some bit of information that only if they get together they can retrieve by measuring, but if they are separate they cannot measure. Then there are some certain states which have very little correlations, however they still have a very large mutual information, and this tells you the level of secrecy. That's why it's used in quantum information, this mutual information. But this is a measure, as I mentioned, of correlations. You can think, intuitively, that this is how much I learn about the second system by measuring the first system, something. That's and it bounds all possible correlations. It's not a measure of entanglement, because you can have a state which is not entangled, but still has mutual information. However, if your state is a product state, so you have in your density operator, it's equal to some density operator for the first system and some density operator of the second system, then it's very clear that the SAB will be the sum of the entropies, and therefore this equals 0. So if you have no correlation whatsoever in the product state, mutual information is 0, and as long as you cannot write things like that, then you start having mutual information, meaning that you have correlations, and these correlations could come maybe from quantum or maybe from classical point of view, but that's a measure of correlation. Now, so if you have many body systems, then you can do the trick as before. You can consider a bipartite system, just consider the whole lattice, the region A, and the complement. Then it's like if you had two systems, and then you can compute mutual information between the system A and the rest for different partitions. And as we will see, again, if you have this quantum mutual information for equilibrium state that is very small, then you can describe the systems very well. But as long as you can have mutual information which is very large, then you cannot describe, or we will talk about that, but it's related to the possibilities of using classical computation or quantum computation for solving the equilibrium problems. Okay, so summary, and from the quantum information point of view, later I'll talk about quantum computation, but now it's quantum information. We have entanglement, we have mutual information, and this tells us about kind of the correlations that are in our system for pure and more general for mixed state. So maybe some of you notice that if I have a pure state, because you can still have mutual information if you have a pure state. If I have a pure state, then the entropy of the whole system is 0. For pure states, the entropy is 0. The phenomenon entropy is 0. And the entropy of the second system is the same as the entropy of the first system. So this means that the mutual information for the case of pure state is 2 times the entanglement entropy. So the mutual information has the property that for pure states it reduces to entanglement entropy. Or if you want, you have a thermal state and you have a 0 temperature state, and you compute the mutual information for any bipartition at 0 temperature, but you will get this entanglement entropy as long as you have a unique ground state. Okay, so moving on to area laws. So now I want to take together the lattice systems and the problem that we were considering, and now these entanglement correlations, and try to make statements about the entanglement that is present in this main body system that I told you before. And you will see that for the second and third lecture, this will be important because, as you will see, if we have little entanglement, then this will mean in some cases that we don't need quantum computers, and if we have too much entanglement, then we will need quantum computers, and sometimes that we have a lot of entanglement, not even quantum computers can deal with it. But anyway, so this is what I'm going to describe as area laws, and you will see why where this picks a name. So now I go back to the lattice. So I have the lattice, which I will represent like this 2-dimensional lattice, but could be any dimension and could be any lattice geometry. And imagine that I have a pure state in this lattice, for example, because what I did is that I started with some initial state. I give you the Hamiltonian, and I compute the dynamics, and after some time, I have a certain state, and this state is started with a pure state, will be pure, so I have some state describing this many-body system, which could be fermions, bosons, or whatever. And, all right, now, or it could be just a zero temperature state, if there is no degeneracy, the ground state of the system, the state at zero temperature could be the one. And then I'm going to ask questions about how entangled this state is. And so what may happen is that this state may be very entangled or very little entanglement, and this is what I will relate later on to the fact that we need quantum or classical computers. And so I have to define what do I mean by very entangled or very little entanglement, and this will be, that will say that it's not so much entanglement if it's an area law, and it will be very entangled if it doesn't fulfill an area law, which is what is called a volume. So for that, I'm going to define a sequence and then assign an entanglement to the sequence, and depending on how this sequence, this entanglement grows, depending on this sequence, then I will say that you have an area law or not. So my sequence is that I'm going to take regions containing some qubits that I call A and complements. And I'm going to look at the entanglement of the region with the complement that I defined before with the entanglement entropy. So I take a region A and I compute entanglement entropy for this region A, for E1. Then I make it bigger and I compute the entanglement, which is, again, the entanglement between the qubits that are in this region and the ones that are outside. And I compute A2. And continue like that. And let me imagine, just for the sake of the argument, that my system is infinite. Okay, so I can grow without touching the boundaries. And now, this entropy should typically will grow. And if you take a random space, so if you would go to the Hilbert space and give these coefficients, these 2 to the n coefficients, random numbers that fulfill the normalization condition, then the entanglement will be an extensive quantity. Will grow like the number of particles that you have inside, will grow like the volume. So if this is the case, so if this quantity is larger than some constant, and then the number of particles in A, then we say that it fulfills a volume law. So you have to define mathematically property, but that's, I'm not going to enter the details here. But if it grows like it's extensive, then we say that there is a volume law of entanglement. And if the entanglement is upper bounded by some constant, and the number of particles that you have at the boundary of the region A, then we see that you have an area law. Okay, so again, what this means is that now I compute entanglement, and then I will have certain number of particles here, and imagine that the entanglement is only proportional to the particle that I have in the surface of that. If it grows only like the surface, I say that you have an area law, or less. The surface or less is an area law. And if it grows with the volume, it's volume. And this, I would say, that has little entanglement, because it only traces this is with the area, and this, it has a lot of entanglement. And now you can take the problems that I mentioned before, and yes, the dynamics or the ground state, because these are pure states, and then you can analyze for many body systems whether you have volume laws or area laws. And the first thing is that if you have dynamics, so remember that one of the problems was the dynamics. So it means that the state psi is built like it's built and as an initial state in which you evolve with the Hamiltonian. So typically, and one has to define what it typically is, after some time, then they will fulfill this volume law. And so I will write it here, so it will be volume law.
It has to do with the interaction, which is...
They have to interact, otherwise there will be no entanglement created, so there is the interaction. And so you can think that the particles that are inside of the dynamics are getting entangled because the interactions are getting entangled with the exterior one, and every particle inside will be interacting, will be entangled with some particle outside. And I say that, I mean, there is a detail here, how long does it take, because this has to propagate from the center to the boundary, essentially that everybody is entangled. So there is some time which is related to what is called the Lieb-Robinson time, the time in which there is a propagation from the center to the sides. in such a way that you reach this volume law entanglement. So that's actually generic. It's not only some particular case, it's generic. So you take a local Hamiltonian like I defined, and then you will take average with respect to possible Hamiltonians. The ones that don't fulfill this volume law after the proper time will have zero measure and so on, so that one can formalize that. But that's nothing. So the claim here is that if you're looking at dynamics of many body system, so very soon you will have a lot of entanglement and you will fulfill the area. And if you want a little bit, I can give you an intuition why this is like that. Imagine that you have a one-dimensional system, and now what you start is with some initial state in which pairs of so particles, let's say, or excitations, propagate linearly. For example, you have non-interacting fermions, and you see that there is free propagation. And so what will happen is that you start with some state which has some local entanglement. Just imagine that two particles are locally entangled. Then they will propagate, the excitation will propagate and will move aside. So from each, let's say, region, you will have particles move to the left and particles move to the right, which are like entangled states. So this could be like something like 0, 0 plus 1, 1, more speaking, where these particles are just propagating. And if in each region this is happening, that's what I told you before, then you see that if I look at some region, the particles that are here are the ones that are entangled to the ones that are outside, and all the particles are here are entangled to the ones that are outside. I mean, these arguments can be made vigorous and so on, but that's the idea. That's the only thing that I wanted to say, that in dynamics, then a lot of entanglement is generated. And in fact, I mean, that's why quantum computers are useful, because they generate a lot of entanglement, because they propagate entanglement, and this entanglement is the one that we cannot simulate with classical. Now, it's more interesting the case of ground states, so zero temperature states. And for ground states, I mean, there's certain mathematical proofs and certain conjectures which claim, morally speaking, that you have area law. And so in particular, you have a gap systems, which I will define in a second. Then there is an area law. And if it is gapless critical, then you have some area law, maybe plus logarithmic corrections. And so let me tell you what is gap system, what is gapless or critical, and let me tell you why this is the case qualitatively. And then what I will do is that later on I will prove something more mathematically about area loss in the context of mutual information. So now let's talk about the Hamiltonian that I gave you before, this many-body Hamiltonian that is local that I gave you before, and then you can look at the spectrum, so all the eigenvalues of the Hamiltonian, and then you can draw it like that. So this will be like the energy eigenvalue, so this will be the minimal energy, it corresponds to the ground state. Then there will be the first excited state, second excited state, and in fact, since the dimension of our Hilbert space is exponential, it's 2 to the n in the case of qubit, then this number of states that are here are 2 to the power n. And so in the spectrum, yes, I mean, we'll draw what are the states, and you can look at the difference between the ground state and the first excited state, and this is called the gap. And now, a gapless system is a system in which you grow it, so you make a lattice bigger and bigger and bigger and bigger and bigger, and this gap is lower bounded by a constant. So it means it never closes. Okay, that's a gap system. It's a one for which their excitations always cost a bit of energy, even in the thermodynamic limit. Okay, when you have n quantity. These are gapped. Now, for critical systems, so this is typical the phases of matter, I'm not going to talk about that, are gap phases and are connected through critical points, so phase transitions. And I think
you normalize the energy.
no, this is not normalized, this is extensive energy. Extensive energy without normalizing, because otherwise there is no gap. No, this is the extensive energy. So the spectrum, if I have local Hamiltonians, go from minus n to n, it's proportional to n, and there is a constant gap. Now, if if you want to say, anyway, so probably, in transitions. So what happens when you go through a phase transition is that this gap closes, and in the thermodynamic limit closes. So typically you have a critical point that is described by some conformal field theory. Then closing of the gap is case with n. So this gap is like 1 to the power n to some power which is a critical exponent. And so these are gapless systems. And for this gapless system, then there are logarithmic corrections, meaning that it's not bounded by n of the perimeter, but n times log n in one-dimensional systems or two-dimensional systems. Okay, something that this statement has been now regularly proven for one-dimensional system, certain two-dimensional systems, but basically there are not known counterexamples. And so that's the idea. So what it means in practice is that if, as long as this is true, that we have volume law for dynamics and area law for ground states, is that the ground states have little entanglement, whereas the dynamics have a lot of entanglement. So it seems that maybe for ground state we don't need quantum computers because they will not generate too much entanglement. Whereas for dynamics we will need quantum computers because there will be no way that we can cope with this entanglement with classical systems. So I will mention that later on when I talk about the classical and the quantum algorithms. So since I don't have time to tell you about the whole story about that, what I'm going to tell you now is for the maybe more interesting or less interesting state of finite temperature, for which one can prove area laws mathematically, and I will prove it so that you understand where it is coming from. But maybe before that, so I wanted to say, so where is this area law? Why do you have an area law? And the reason is relatively simply qualitative. You can make it also quantitative. But the reason it was shown very long ago by Matt Hastings that if you have a gap, so you have a gap system, then all correlation functions decrease exponentially with the distance. All connected correlation functions. So you take a correlation function between two observables, and now you take take them farther apart, and you compute this correlation function. You have a gap system decreases exponentially. So what is happening, if you want, is that you take your system, and you take the region A, is that now the correlation is only some length, and this is called correlation length. So there can be only entanglement within some correlation length. So you have a system, only the particles that are within some length, which is called correlation length, which will entangle, independent of the size of your system. So you make it bigger and bigger and bigger, then the only ones that will be entangled will be the ones that are around this region, and therefore this is where the area law is coming from. So that's the, basic idea of the area law, where it's coming from, qualitatively. To make this argument quantitative is difficult, and in one dimension can be done, and in higher dimension then you have to go through spatial cases, but that's the more. But so I wanted to mention is that actually now there's a kind of stronger result, which is in the case of thermal states. So now if we go to gift states or mixed state, and let me consider now the same situation in which I have.
Excuse me, in the case of gapless critical, why the articles?
Well, because you have a power law correlations, and you integrate power law correlations, it can give you logarithms in the case with certain power. If the power is larger, then it will give you area laws. This is why I say, by possible, in some cases there is power law, area, it is with logarithms.
So, sorry, let us try to concentrate questions at the end of it, because there is some room.
Okay, good, whatever. So now I want to consider the thermostates. So now I have finite temperature. So this beta is not infinite. Okay, finite temperature. And then I have a gift state, rho, which I remind you that is t to the minus beta h, properly normalized. And then what I can look in this case is not at the entanglement, but at the mutual information. So I can see how the mutual information scales as I make my system bigger and bigger and bigger. So I can do the same exercise. I take a region A1 and I compute the mutual information in A1, the rest, or A2, or A3, and so on. And I can define that if it fulfills that is larger than some constants on the number of particles that have in A, this will be volume. And this is smaller than some constants times the number of particles that I have at the boundary, this will be an area law. And so So let me now prove that all states fulfill an area law with that. Because it's a very simple proof that I think members can do as a kind of exercise here. And I'll have to use one mathematical fact that I'm not going to prove, but I mean, you had some course on statistical mechanics, then I'm sure that people prove it, is the following. Imagine that I consider what I call the free energy, F of rho. F rho maps density operators to numbers. Okay, so you give me a density operator, and I'll give you a real number after that. And the mapping is very simple. So what you have to do is to compute the trace of H rho minus T times the entropy of rho. Well, this is the Von entropy that I defined before. That's the expectation value of the energy. So this is like the energy. So it's energy minus temperature times entropy. That's how we define the mutual information. And now you can put here this different density operator. You can take a density operator corresponding to something or something and something and something. And let's imagine that my goal is to minimize this free energy. So I want to find what is the minimum with respect to all possible density operators, so all possible positive semi-definite trace one operators of f of rho. And I want to find what is the argument of this function. So I want to find the density operator which minimizes that. And it's well known, it's a mathematical theorem, that this is just the Gibbs state corresponding to this Hamiltonian, minus beta h divided by c. So if I minimize the free energy with respect to all possible density operators, the one that minimizes the free energy is the Gibbs state. That's actually how you define the Gibbs state, in fact. And so you can see it as a definition, but I mean the fact that it has this form is just coming from this theorem. And that's the only thing that I'm going to use now for this proof. So what I can do is that you're giving me the region. I have the density operator rho A. I have divided region AB. Here. I call this state rho AB because mentally I have separated the region A and the region B. I'm going to compute rho A, which is, so I have rho AB. This is the Gibbs state. Rho A is just the reduced state of rho AB. So this is the reduced state for system A. Rho B is the reduced state for system B. So it's like if I trace system A. And now let me use the free energy of rho AB is the minimum one. So if I put any other density operator, it has to be larger or equal. So this is smaller or equal than the free energy of the state that I get from A and B. Just taking the reduced states and producing a product state. Okay, so you say that just because of that, the minimum before that, so it has to be smaller than any other one. And now you use the definition, let's use it. So this will be the trace of H rho AB minus T times the entropy of AB, when we call it rho AB. And this, the free energy is additive. So this is the free energy of A plus the free energy of B. So this will be the trace of HA, the region, the Hamiltonian only in region A, plus the trace of the Hamiltonian in region B, minus T, the entropy of A plus the entropy of B. And now we move this on the other side. So I will have on the right hand side T of entropy of A. So let me move it to this side, to the first side. So this goes in the positive side. So it's T times entropy of A plus entropy of B minus entropy of AB. But this is the mutual information. T times the mutual information. And this is, let me do it right. This is smaller or equal than the trace of HB, but this Hamiltonian is just the Hamiltonian of the everything that is happening in A plus everything that is happening on B, minus or plus everything that is happening between A and B. So this would be like interactions that are inside A, plus interactions that are in B, plus the ones that go across the boundary. And now, from here, if I did anything wrong, then you see that this first term will be the Hamiltonian A with row A. So you can trace B because it doesn't depend, so it's a trace of HA row A. So this term cancels this one here. This term cancels this one here. And the only thing that remains is the Hamiltonian in the boundary. So if you count how many terms are there, are just boundary terms. And so from here, it comes that the mutual information, you go to the other side, then it's probably made a mistake with pluses and minus somewhere, but that's the basic idea. That you prove it just with a very simple rules. And so this means that if we have thermal equilibrium, then at the end we will have an area law. This area law, this constant now depends on the temperature, and if the temperature goes to 0, then this constant goes to infinite. So it's not useful for 0 temperature, but for any finite temperature, then this proves this area. Okay? Okay, so with that, this makes the connection somehow that I wanted to have between entanglement and correlations and many-body system, and the conclusion that in thermal equilibrium, there is little entanglement or little correlation because we feel an area law. Whereas if you have dynamics, then you have volume laws, you have a lot of entanglement in the system. Okay, so now I want to finish this part of the lecture, just talking about quantum computation and complexity theory. So what I want to now very briefly, because I guess that you have heard that before, talk very briefly about quantum computation, and then I want to talk about complexity because I'm talking about difficult, and this is easy for a classical computer, this is easy for a quantum computer. So I want to define what is easy and what is difficult, or more precisely, and this will be the complexity theory. So I think it's for quantum computing. Okay, so in a quantum computing, so what we have is a set of qubits, like we have in many-body systems, that we typically represent as dots. And then we have time, which is running always from left to right. So for each of the qubits, we have the timeline, which goes like that. And a quantum computation, what it does is it transforms the state of the qubits according to the laws of quantum physics, which is according to some unitary operation. So we represent it like that. This is some unitary operation. And so you start with a certain initial state, which typically will take the state in which all the qubits are in 0. This is the state that I wrote 0, 0, 0, 0, 0. Then at the end, the state of your quantum computer would be times psi. And in a quantum computer, what you do is that you evolve or apply something to have this unitary operation, which I will describe in a second. And at the end, you measure your qubits. You make a measurement, which represents like something like that, some dial, each of them. And so typically what we do is that we measure sigma c observable in each of them, or if you want to measure in the computational base, we measure if the state is 0 or 1. And so out of that we measure, and then we get an outcome, like n1 and n with certain probability Pn. And so the goal, of course, is that if you have now a problem that you want to solve, let's say you have an optimization problem, or you have a many-body problem, or you have a factoring problem, or you have something, then what you would like to do is engineer this unitary operation in such a way that when you get the outcome with a very high probability, you get here the solution to the problem that you want to solve. So that's the art of quantum computation. However, now how do you implement an arbitrary unitary operation? And that's what quantum computation copies from classical computation. In classical computation, you have a Boolean function, you have zeros, you map it into zeros or ones. This Boolean function, any Boolean function, can be decomposed in terms of universal separate gate. For example, NAND gate or XOR gates are universal, so it means that the concatenation of these gates can generate any function that you want. The same thing happens in quantum computation, is that there is a set of elementary gates, called a universal set of gates, such that by concatenating these gates, you can generate any unitary transformation. These gates, I mean, there are different sets. The typical set of gates would be what we call a control knot gate, which is a gate acting on 2 qubits that we represent like that. So, and this has a truth table, so you can define this is a unitary operation. So a unitary operation can be defined by the action of the elements of a basis. So it can tell you what happens with any element of the computational basis just by the superposition principle, linearity. You can see what is the action on any element. So this has the table that acting on 0, 0, it has 0, it doesn't do anything, except if the first qubit is in 1, that flips the second qubit, and this is what is called control knot. So if the first one is in 1, it controls whether you do the knot operation to the second one. So that's control knot gate. Then there are single qubit gates, and these single qubit gates, we represent it like that. We just take a qubit and change arbitrarily. So this is an element of SU2, and so this maps and state 0 into linear superposition, cosine theta divided by 2 times 0, by sine of theta divided by 2, 1, and 1 is minus sine of theta divided by 2 to the I phi 0 plus cosine of theta divided by 2, 1. And one can easily prove, I mean, this is what you do in quantum computation, that a concatenation of 2 qubit gate and single qubit gates can generate any unitary operation. So any unitary function can be decomposed. In fact, you don't need all the unitary gates, you need 2 of them, with 2 of them. So which is the S gate and the T gate, and that's enough, you can generate everything. And so what it means is that now you have a quantum, or a problem that you want to solve with a quantum computer, and you know what is the unitary operation, you still will have to decompose this unitary operation into single and 2 qubit gates. At the end, the circuit that you have to give me will be something like that. You have 2 qubit gates here, maybe some unitary operation here, and some 2 qubit gates here, some unitary, this will be the circuit. Now, the catch here is that how many gates do I need in order to implement an arbitrary unitary operation? And can be proved right away just by counting numbers, but it's exponential. So this means that I will have to do, typically, 2 to the n gates. Now, the time of performance of this gate in a quantum computer is measured in terms of what is called the circuit depth. So what you can do is take this, cut it in steps, like that, and count how many steps are, and that's what is called the circuit depth, which is basically, so you can act in parallel on qubits, is the time that it will take, proportional to the time that it will take the quantum computer. And so in general, if you give me a unitary operation, then the depth of your circuit will be exponential in n. So the quantum computer will take an exponential time to solve an arbitrary problem. However, there are some problems for which people have figured out how the unitary operations that solve the problem only need few gates, polynomial depth. For example, for the factoring, famous factoring algorithm, for pair equations, there are a set of problems for which we know that you need only a polynomial set of gates in such a way that you have a problem, you find what is this, how you want to solve, you make, this is called quantum circuit, so it's a circuit that's built of quantum gate, and the number of gates, which is the computational time, only grows polynomially, linearly or quadratically to the central system, and then this is feasible in a quantum computer as long as the quantum computer works. Right? I mean, unfortunately, the ones that we have don't work, so it's not possible at the moment, but don't work ideally, they have errors, and it gives another problem to the setup, but that's the basics of quantum computation. Okay? So now, if you want to solve a many-body problem, the problem that we're dealing here is a quantum computer. So what you will have to do is to formulate the problem that I gave you before in terms of gates, and then give me the gates, and then I will count the gates, and I will tell you whether you have a good algorithm or a bad algorithm. So it takes an exponential time, it will not be useful. It takes polynomial time, it will be very useful. And okay, so I think that with that, I'm done with quantum computing. All right. And now I wanted to talk about complexity. Okay? So, because we could do the same thing with a classical computer. Okay, so you want to solve the problem with a classical computer. At the end, you want to compute something like a Boolean function, I mean, going from bits to bits, and you can count how many elementary gates, and this will tell you, so what is your circuit depth, and it will tell you how it depends on the system size. It will tell you whether it's efficient or not efficient. And complexity theory tries to make sharp definitions to be able to compare now different ways of solving problems in a rough way. So this is what I'm going to briefly describe here. Okay, so computer scientists would like, given a problem that you formulate, to see whether this problem is difficult, is it feasible or not feasible, and this is why they divide the problems. And the way they have to do it is a very clever way, when you're not a computer scientist, so they formulate all problems as decision problems. So these are problems which have an answer which is yes or not. And then you compute how many gates you have to do in order to solve that problem. And depending on whether this, and you count this number of gates as a function of the size of the problem, the number of bits that you need in order to encode the problem. And if this grows exponentially or polynomial, they have different classes, which is a kind of a graph description of the difficulty. And then you can make something a little bit more fun and fun and fun. And here we go with the description. So I'm not going to write it mathematically because I don't have time. But the fact that you can formulate problems as a decision problem, I mean, at the beginning is surprising, but actually it's not surprising. So, for example, imagine that you want to factorize a number. Factorize a number, if I did like that, I give you a number, I give you two factors. This is not a decision problem because you have to give me the factors. But I can have a decision problem, which could be, for example, is the number factorizable? Right? The decision is yes or no, the answer. Or I can have a more clever way of a decision problem, which is there a factor smaller than 10,000? That's a decision problem. The answer is yes or no. And you see that if I'm able to solve this decision problem, yes, no, then I can solve factorization very efficiently and even find the factors. Because I can do bisection. I can say, I have a number, I know that if I want to factorize, the largest factor can only be the square root of the number. So I can tell you, is there a factor smaller than the square root of number? Yes or no? And if you can solve it, you say yes. Okay, then I know that. Then I can cut half. And is there a factor between half or smaller than this square root divided by half? Yes or no? You say yes. And cut half. And half of the half, this grows exponentially fast to the point, so you can find the point. So this is why now you can formulate any problem as a decision problem and use it in practice. So this is why they classify decision problems. And now, these decision problems, there will be some of them for which you can solve them in polynomial time, meaning that if I have to use n bits in order to store the problem, for example, factorization would be the binary notation of my number that I want to factor. So if you look at the computational time, which is the depth of your circuit as a function of the number of bits that I need, then this can grow maybe linearly or quadratically or cubic. Let me say that it's polynomial. And so this makes the class of problems which can be solved in polynomial time. And so if you take all possible problems, then there will be some of them which should be. And so basically these are the problems that we can solve efficiently. For example, multiplication. Multiplication written as a decision problem, right? But this is one of them, which is easy. Now, There are problems which are not in P, and so there are problems, for example, that will take an exponential time, and this would be a class that I don't know how to describe, it's called exp. There would be another class of problems that maybe don't need an exponential time, but need exponential space. So you have n bits, and then you have a space to 2 to the n, and you can do things in parallel. There's another class which is called B-space. Okay, there are different classes which are much bigger than this one here. But then the one which is especially interesting, which are called NP problems. These are decision problems that cannot be solved in polynomial time, but can be checked in polynomial time. Okay? So for example, this is a class which contains P. And one of these problems is the factorization problem as a decision problem. So why is an NP? Because it's very difficult to factor numbers. There is no polynomial time algorithm that given a number will give me a factor. However, it's very easy to show that there is a factor if you give it to me. I just have to divide and see that the remainder is 0. So the problem in P is difficult. Factoring is in NP because even though it's difficult to factorize, it's easy to check a factor. So these are the ones that giving computer science, you have given a certificate, so giving a factor in that case, giving a certificate, you can check in polynomial time whether there's a solution or there is no solution. So these are the typical problems, and there are more classes. But what is important here is that a quantum computer, we want to put it in the setup, and the first thing is that the quantum computer is not deterministic. So a quantum computer, when you measure at the end, probably you have a high probability of getting the result, but it will not be for sure. So this is why you have to extend this definition, also classically, to include probabilistic solutions. And this is a class that is well known classically, which is called BPP, non-error probabilistic polynomial, which is the class of decision problems that you can answer correctly with a probability larger than 2/3. And you say, why is 2/3? Well, it doesn't matter. Because you can, running several times, you can exponentiate this number. You can make it as large as you want, simply by repetition. So for example, if you solve something and then you get the solution with the yes, no, with a probability 2/3, you repeat it, and 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 repeat it. And you do it many times. So the probability that half of them plus 1, and you have to take majority vote, the probability that half of them are wrong, or more than half are wrong, with the probability is 2/3, and it goes down like 1/3 to some power, so go exponentially. So you can boost it as much as you want, just again with a kind of logarithmic number of repetition, very few repetitions. So in practice, these problems are very interesting because even though you don't get the right result, you can get it with as much higher probability as possible. Okay, so as I mentioned before, that there would be more sets that I'm not seeing here. These are the relevant ones. And now, what happens if you try to solve this decision problem with a quantum computer? Then you have a different class, and this class is called BQP. And it's very easy to show that BQP contains BQP. And the reason is that any classical computation can be written with quantum circuits with a quantum computation. So quantum computing includes classical computation. It's very simple. You just work in the computational base. You have to use a trick because of the fact that it has to be unitary. You have to add some kind of additional qubit to make sure, but that's possible. And so this means that this BPP contains BQP contains BPP, and there are some problems here that we know that like that. Put it. Some problems that we know that are not in BPP, but are in NP. For example, factoring is one of them. Factoring. There are few of them. And then there is the one of quantum simulation. Okay? So the one that I tell you before, which is, if you want, I give you a Hamiltonian. I tell you about dynamics. And one-to-one, your goal is to compute some expectation value with some error epsilon, or to tell me if some expectation value is smaller than 0.3 minus epsilon, or 0 plus, okay, it's smaller than that. Right? This is a decision problem. So this decision problem can be solved with a quantum computer, as we will see later on with these quantum algorithms. However, there is no way that we can solve it efficiently with a classical computer, not even probabilistically, and there is no way that we know that it's even possible to check it. So it's not even in NP, right? So this is why this is here, the quantum simulation for some of them. Okay? So what we also believe, now this in computer science, there's nothing proven. So it's proven by existence. So if there is an algorithm that does something, so you discover an algorithm, you may change the class. So it may happen, for example, primality test. Primality test is I give you a number, and I ask you, is it a prime number or not? Primality test was in BPP, but not in P, for a while. And in 2006, PhD students found an algorithm, and now it's in P. So as a function of time, this changes, because it depends on the algorithm. And so in fact, I mean, it's not known even if P is equal to NP or not. That's the $1 million question. So you answer this question, you will get $1 million. But we don't know anything else between the fractions. We don't know if BPP is equal to BPP. We don't know if BPP is equal to P. We don't know if NP is equal to P. We don't know if this quantum simulation is in NP. We don't know methods of doing of checking, but there might be exist one. So that's the situation. And then there is another class, which is the one that we cannot solve efficiently with a quantum computer, but we can check efficiently with a quantum computer. So it's the same thing as between P and NP. One is the class that you can solve efficiently, NP the class that you can check efficiently. There is the class of can you solve with a quantum computer efficiently, BQP, and the class that can check efficiently with a quantum computer, which is QMA, which contains everything else. And, okay, so I could come back to that. QMA is a problem that can be checked with a quantum computer, but cannot be solved in general with a quantum computer. For example, is there, if I give you a Hamiltonian, is the ground state energy of this Hamiltonian smaller than some number? It's a decision problem. That's hard in general, we mentioned that later on, to solve with a quantum computer. However, if I have a quantum computer and I give you the state, like a certificate, you can just measure the energy and check that it's below that. So you can check with a quantum computer that it fulfills that. Now, just to end up, in each of these sets that I defined before, there is a subset which is very important, that is called the ones that are complete. So this is, for example, there's a subset here which is NP complete. In QMA, there is some of them which is QM made complete. In BQP, there is a set which is BQP complete, and so on. And so these are the problems that are in the class in such a way that if you find an algorithm for them that changes the class, then all the class changes. This is why it's called complete. Or if you want, any problem which is in NP can be reformulated as a problem in NP complete problem, and therefore you solve that. Then, since you can translate it with some polynomial time overhead into this class here, then you solve this problem. You show that this problem is in NP, therefore is in P. Then automatically P is equal to NP. The whole class collapses. So you want to convince a computer science that that problem is very difficult. Then you show this computer science that is, for example, NP complete. Because maybe there is a problem that you invent and nobody look at it, and that you say, oh, it's in NP. And this person comes after 3 hours with an algorithm and say, well, I mean, that's very simple to show that it's in P. However, if you come with a problem and you show that it's NP complete, then it will be very hard for this person to show that this problem is not difficult. And if this person will be able to show, then you ask him to, or her, to share the $1 million because it will solve this question. So that's why in these quantum simulation problems, some of them will be QMA hard or QMA complete. So some of the problems that I will mention will be in this class. And so therefore, if one quantum simulation will be easy with a quantum computer, this automatically would imply that all of them are, let's say, in BQP or in P or something like that, would collapse everything. So there is a good confidence that those problems are difficult. And so that's the philosophy of this complexity classification. You classify the problems, you find a subset that are very difficult, the subset of beliefs that these things are difficult, these things are simple, and then you try to map problems to the ones that are discomplete, and then it will give you some kind of security that these are really difficult. So how am I doing with time?
We have something like 10 minutes, 15.
Okay, very good. Okay, so then I will mention okay, so now in this complexity I'm going to talk about many-body problems and what is the complexity classes, and then I will argue that that's what people using computer science working on many-body physics, then they use these arguments and so on. However, I want to argue that if you're interested in the problems that I told you at the beginning, the ones corresponding to many-body physics in high-end matter, it actually may escape some of this classification, because they are very specific problems and very peculiar problems. And so this is why, later on, then this will give some arguments for this quantum computation and quantum simulation. Okay, so I want to talk now about many-body problems and talk about this complexity. So the first thing is dynamics. Okay, so I will not formulate it as a decision problem. I mean, you do it very informally, but you understand that everything that I say at the end could be formulated as a decision problem. But dynamics is you're giving a Hamiltonian. You're giving some initial state, a description of an initial state. For example, typically this is a product state. So you're telling me that this is the 0, 0, 0, 0. You're giving me the Hamiltonian, which is a description of the Hamiltonian, and this description always, for this, you assume that all of them can be encoded in n bits of information, so polynomial number of some bits of information. You're specifying some time. You're specifying some observable, and you give me a prescribed error. Okay, so the goal is to start with some initial state and to compute the expectation value of this observable with a precision epsilon, so that you're sure that you will not make an error with value that is epsilon for some CT for this Hamiltonian. Okay, so this problem actually is very simple. Sure, I'm not going to do that. Maybe I do it in the last part. Is that this problem can be built with a circuit. So I can solve this problem just by making this control knot with a quantum circuit. This will come later on. And that the computational time with this quantum circuit that I will build for the class of Hamiltonians that I have. So this is the computational time that scales like, I'll write it like that, scales like n squared, t squared, divided by epsilon squared, and that's it. Okay? So it scales polynomially both with the number of qubits, so the quantum circuit that I will give for that later on, it scales like n squared, then t squared, and something like that. And as I advance, the idea would be to prepare the initial state in your quantum computer, then compute an approximated evolution by doing some gates, and at the end measuring this observable. Then you repeat it many times, and the expectation value, because of the law of large numbers, will converge to the exact expectation value, and the number of repetitions that you have to do, if you have some probability distribution, it will give you 1 over epsilon squared. And you will have to have an overhead because of these gates that are not corresponding to the system. Actually, 3 or 4 years ago, there was a better algorithm than the one that I will give here. It's very complicated, I will not explain here. But actually, there is an algorithm that is better than that, that's proportional to n, proportional to t, and proportional to log 1 over epsilon. So it's extremely efficient. So this algorithm scales polynomially with n, be for any fixed t, it will be in BQP. However, there is no classical algorithm that is known that would take a polynomial time, even probabilistically, so it's not in BPP. Okay, so this is the dynamics, and it's a problem which is extremely well suited for a classical computer. And it's so well suited that now imagine that you want to solve it with a classical computer. What will you have to do? You want to solve it exactly. So you will have to use a memory in your quantum computer to store all these complex coefficients that grows exponentially. And it will grow also exponentially with time, because as I mentioned before, for each of the coefficients, you will have, in order to obtain them, you will have to do a computation at least. Since there's an exponential number of coefficients, the time grows exponentially. So you see that it's exponential in memory and exponential in time for a classical computer, whereas it's linear in memory and linear in time with a computer. In fact, now we can play the game and say, what happens if I try to use a classical computer and I limit the memory? For example, I have at most 10 to the 80 bits. No? We cannot have more in our universe. Or you say, let me allow a number that the memory grows linearly with the size of the system, like we have in the quantum computer. And then what it happens is that the computational time that it takes doesn't grow exponentially with them, but grows super exponentially with them. And so this shows that the dynamics is a typical problem for which a quantum computer can help you a lot, because you have not even exponential, but if you put some limitations, it's even worse than exponential with a classical computer, but with a quantum computer, it's very, very standard. Okay, so dynamics is a good one. So what about now ground state? So the ground state is that you're giving a Hamiltonian, you're giving an n. So here I forgot to say that there is an n. So always there is an n, and you're fixing the number, and you want to see the spinning with that. You're giving a Hamiltonian, you're giving some observable, and you're giving some epsilon. Okay, so you want to compute the expectation value of some given observable, single particle or correlation function observable, with a precision epsilon, and with a Hamiltonian that is given, which has the form of the one that I told you, these local Hamiltonians, in the way that I define them here. So, as a decision problem, this is QMA hard. Okay, so it's here. Which is QMA hard. So it means that that's very difficult to solve these problems in general, even with quantum computers. But that's not so weird, because we can take now, let's forget about quantum problems and quantum computation, and let's take classical problems and classical computations. And let's take, for example, the Ising model. I mean, the Ising model with random coefficients. Okay? We have nearest neighbor interactions, sigma c interactions. So as a classical model on a lattice, that model, it's hard, it's NP hard, and depending on how you rephrase it, is even a class that is more difficult than this one here. For example, you want to compute the partition function or things like that, is extremely hard. So the fact that there are problems that are quantum, actually it's NP complete. So there are problems that are quantum that are very difficult. It's not weird, because there are classical problems which are very difficult and that are NP hard. And we don't believe that the NP hard problems are part of PQP. Now, what about thermal? So thermal equilibrium. Well, it's the same, but now you're giving some temperature as well. Well, this problem, of course, includes the zero temperature, so therefore they have to be as hard as the finite zero temperature. So it's also clearly hard. So they are, in general, difficult. Now, what one can show is that if the temperature is sufficiently high, then actually they are in PQP, and if this is even higher, they're in BPP. They can be solved classically for very high temperatures. So for infinite temperature, it's trivial. So what? Now, is this a concern? And what I want to mention is that, of course, these problems are the more general problems in which you have Hamiltonians that don't have the symmetries of your problem. These are problems like spin glasses, that you have interactions that are completely different, and these are the ones that are QMA hard. However, the problems that I was considering initially, that we're considering in physics, they are not as general, so they have symmetries. And so, for example, they are homogeneous, typically, translational invariant, if there is no randomness or something like that. They may have rotational symmetries, and they may have some other symmetries. So the question is, what happens now with problems that have symmetries? So you impose the fact that the problems that you're solving are not ground state of translationally invariant thermal equilibrium for arbitrary Hamiltonians that could be completely different in different lattices, but they are homogeneous with symmetries. And then this is where you can show that some of these problems are in BQP. And so when I talk about quantum algorithms, then I will tell you that if some conditions are fulfilled, that, I mean, we expect to have these conditions in all physical problems of interest, then both this one here and this one here are in BQP. And then I will give you the quantum algorithms that solve that. And still these problems are not in BPP. So these are problems which are hard with classical computers that will be easy with quantum computers. So the summary of all what I say is that if you consider problems in general, not physical problems, then the dynamics in quantum computer is simple, and with classical computers difficult, but ground states or thermal equilibrium may be difficult for both classical and quantum computers. If you add the fact that you have, this corresponds to some physical situation that we typically encounter in problems in physics, then they are even simple quantum, but still difficult classical. And that's why, I mean, this field of quantum computation for these quantum many-body problems gives you some hope that things will work. Now I wanted to comment a couple of things that I think that are relevant. Maybe I repeat them when I talk about quantum algorithms. So you can see now, you can hear all the noise that quantum computation is making, saying that with the quantum computers we can solve optimization problems more efficiently than classically. So actually optimization problems, they're here typically in P-hard. And with a quantum computer, we cannot bring them to BQP. So what we can do is accelerate them a little bit by the square root or something like that. So in one takes 2 to the n, in quantum computers 2 to the n half, in this kind. So there is some acceleration which is relevant, but it's not as big as the one that we have for quantum many-body systems. So for quantum many-body systems, we have a huge acceleration. In fact, in the dynamics, as I mentioned before, it's not only exponential, it's more than exponential if you take into account the memory. The second part is that now the quantum computers that are being built at the moment, and the quantum simulators, I'll talk a little bit about that maybe, they have errors. They are not perfect, so when we roll these gates, and these are not like that, they have many errors. So now the question is whether in the presence of errors, you can still use these algorithms in order to solve these optimization problems or these quantum many-body problems. And you may understand qualitatively that, of course, if there is a little bit of gain only, it's not an exponential gain. With an algorithm, if you have errors, you may well lose this gain that you have. And that's, I mean, what I would expect that happens with most of these optimization algorithms, that the errors make them that there is not such an advantage, or that it will take a lot of, effort to work against the errors to have this advantage. However, since all of these problems, there is this huge difference between the classical and the quantum, still in the presence of errors, you may still have a hope that you can answer questions that you cannot answer with classical computers. And what I'm saying now, can be formulated more mathematically. Actually, we wrote a paper very recently about the complexity in the presence of errors for quantum simulation. And so there's, I think, from my point of view, a lot of hope for quantum simulation, even in the presence of errors, namely with the quantum computer that people are building at the moment. So with that, I think that I can finish, and so I'm very some questions.
Thank you very much for this very interesting lecture. Particularly, you have shown that one can do quantum information on a classical blackboard. Okay, we have some time for questions. Yes, Keita?
To understand this decomposition of unitary operators into gates, it understands well that if you combine discrete number of gates which involve more than one qubit, and with one qubit, which may depend on a continuous like theta and so on.
Well, I mentioned that this is possible, but actually it's possible to do everything discrete. I mentioned, so maybe I repeat what I said. So you can decompose any unitary operation in a set of what is called universal gate, meaning that the concatenation of this can be the original one. Now this universal set of gate, the one that I presented here, is, as you mentioned, one discrete 2-qubit gate and a continuous, so something that depends continually on some parameters. However, that's not necessary. You can make this discrete. So you can take, yes, 2 of these single qubit gates, and this is still universal. So you can have discrete. Yeah?
But how can you get 2 good pieces out of discrete?
Because you can approximate as much as you want. So there was shown by Titayev many years ago that if you have any gate with a theta and a phi, so continuous for any theta phi, and I give you the gates that I gave you before, with you want to approximate this other gate with an error epsilon in operator norm, then you need only something, a number of original gates which grows like the logarithm of 1 over epsilon. So you can approximate extremely fast those ones. So this means that you can think of, this is what people think in experiments, with continuous, but if you would require discrete, each of them could be take some logarithm of 1 over epsilon. So you want epsilon 10 to the minus 20, so 20 gates, you put something like 20 gates, and then you have it with that error.
Yes, there was a question from there.
We thought that GS ground state problem and the thermal energy problems are GMR unified, but for some classes of instances they are not. And they are hard for the key, so I was wondering, for classical oscillation, so I was wondering if there's an actual effort on finding algorithms, classical algorithms. It's just like there's a branch of research in classical.
Yes. So
that is really trying to find classical.
Yeah. So in fact, there are some set of quantum problems that could be solved efficiently by classical methods, for example, Monte Carlo, but they have some strict conditions, some strong conditions. Whereas the ones that you can solve with a quantum computer are weaker conditions than that. Now, still, I mean, this is, I think that's one of the ideas that is relevant, that this answer that I'm giving to you may depend on time. So you ask me in 10 years, it may be different because somebody came up with a classical algorithm that now can solve some of the problems that quantum computer can solve, or maybe quantum computer can solve problems beyond what we
Indeed, my question was like, how many years are we spending on looking for this?
Of course, there is a long tradition of people trying to solve quantum many-body problems with classical methods, whereas there is not such a long tradition of people looking for quantum algorithms. So I say that in this case, there is a very big advantage. Classical algorithms are much better known than quantum algorithms. So, I mean, for example, I will talk about classical algorithms tomorrow, this afternoon. And in this classical algorithm, I will show that some of the problems can be solved with classical computers. So in fact, this ground state, in one dimension, if you have a gap, then it can be solved efficiently with tensor network methods that we introduced. And this was not known until 5 years ago. So there were some computer scientists who proved that. Okay? So now that's a problem that it was in fact, it was not even in BQP at the time, it was in QMA, and then they found an algorithm that brings directly to BPP. Okay. So these things happen, and right, because it was a new technique, new classical technique, which was brought to the field, and then it allowed to solve some problems that people didn't know how to solve. So this changes with time, and may change with time. However, there are many, I don't know if there are some condensed matter physicists or lattice-based theory
here. Of course, I mean, there is a lot of knowledge there and a lot of methods there that are extremely advanced, right? Classical methods to solve many body problems that are very useful in many occasions. Okay? So probably many of the problems here already can be solved by classical computers. But there are still some of them that we don't know how to solve with classical computers, and we know how to solve with quantum computers.
First of all, thanks for the great lecture. So, my question is, you mentioned a very interesting fact that the thermal equilibrium, there are two facts actually. First, the thermal equilibrium can, if you heighten the temperature, then fall in BQP and then fall in BTP, and you have this trivial argument that the identity is trivial in BTP. And then you showed with a very elegant proof that every gate state follow area law. Are these two facts kind of related or not?
Okay, so the line of argument is that the fact that you have an area law for thermal states automatically implies that they have an efficient description in terms of tensor networks. That's what I will talk about this afternoon. That this exponential memory is no longer used. So this is a polynomial memory. So this already is. Now, the fact that you have an efficient description of a many-body system doesn't mean that you can still solve it classically. It means that you can store it in your computer, but still the time can be exponential. And so that's what may happen. That for some temperatures, you can store it in your computer very efficiently, and you can solve it in another time, but there is some transition temperature at which it gets very difficult, and even some lower temperature at which it gets very difficult with a quantum computer. I mean, we don't know really examples, but we have proofs. So we know that if the temperature is larger than something, then you have efficient, I mean, Monte Carlo will work for that, or series expansion, some classical methods that people have developed. But for low temperatures, we don't know. But what we know, with the fact that they have, what I will say this afternoon, is that we know that there exists an efficient description, so the problem with exponential memory that you need in a classical computer to store the state goes away with the mutual information proof.
Okay.
Hi. So, you cast the problem of the dynamical problem of quantum many-body physics as basically computing expectation values and correlation functions of local observables. And this is efficient. This is great. But do you believe there are other problems in quantum many-body physics that are outside this paradigm, that are not just correlation functions?
Well, there could be string order parameters, right, which are many-body correlation functions, detect of topological phases. So indeed, they are like that. But all of them are product of local observables and things like that. So they can be casted in a similar way. So what is subtle here, that I didn't want to enter that, is when I talk about this error epsilon. I mean, there's a lot of thought behind this epsilon. Because you can have, for example, multiplicative errors or additive errors. So maybe you want to have the observable plus minus epsilon, or you would like to have that the value of the value that you obtain is between, so 1 plus epsilon the real value and 1 minus epsilon times the real value. And the second one is much more difficult. And it's much more difficult because if this value is exponentially small, then it will take exponential time. So for multiplicative errors, not even quantum computing will solve, but for additive errors, this is what it was proven in those. As long as you want to, you have to measure you have to specify an observable that can be measured in, let's say, polynomial time, like this thing. Because if you give me a many-body observable that will be a sum of an exponential number of terms, then it will not, it will go away.
Yeah, so my question is, do you think that there are interesting problems from the quantum many-body point of view that are of this type? Or they are, you can neglect them because after all they are invisible, right?
Right, so there are two reasons why I don't think that they will be interesting. So the first is that it will be difficult to compute, but the stronger reason is that nature probably, it takes an exponential time to do something. It's irrelevant for us. We'll never have done that.
Actually, I have a couple of questions. They are quite general. There is a part of quantum mechanics which is very interesting, in my opinion, which is measuring. Yep. quantum mechanics. Some parts of this theory are still controversial, so to say. This has an impact on quantum information research or even from the point of view of implementations and so on.
Well, the question of problem of measurement is a fundamental problem, but there is a practical approach, which is this calculate, shut up and calculate, Feynman was saying, whoever was saying. And this means that this is what happens in quantum information. In quantum information, this doesn't have any let's say, impact. Of course, I mean, it's very interesting, and the other way around, there might be some impact. So you build big quantum computers or big systems that are entangled, then there are people like Tony Leggett that believe that after some size, then superpositions are not possible anyway. So that there are corrections to that, or Penrose, decoherence-induced, gravity-induced decoherence, and things like that. So these systems may help maybe to give some shed some light in some of these fundamental problems. However, all these, I mean, these foundational problems like local hidden variables, well, non-local hidden variable, Bohemian, Everett, and so on. All of them, by definition, have the same predictions about quantum physics, because otherwise you could distinguish by experiment, but these are not distinguishable by experiment, and therefore, what we say here is valid for all of them. So we compute it, we give you, and then you can have your favorite interpretation to interpret the results, but it will not have impact on what a quantum computer can do.
Also, another clear that quantum computer in the future will be something like a hybrid object, both classical and theoretical. Is there some kind of mathematical formalization of this fact that you have this sort of hybrid object?
Well, I'm not aware of mathematical, because you can embed always classical into quantum so that the whole quantum would include classical. What I can tell you, and I think that tomorrow I will talk about a hybrid algorithm. So there will be a quantum algorithm to solve finite temperature that is hybrid, in the sense that it will be like a Monte Carlo method, classical Monte Carlo with a classical computer. And I will explain that Monte Carlo methods have a problem which is called the sign problem, that they don't work for certain problems. And so this means that they cannot sample. And so what I will explain is how a quantum computer can overcome the sign problem, can compute the probabilities that you cannot compute, and therefore it could use a classical computer to sample, and only the quantum computer subroutine to compute things. And there are several algorithms like that, which use the quantum computer only to do certain things that are difficult for the classical system. There exist algorithms like that, but I'm not sure if there is a formulation that would be like a Hebrew formulation of that.
Okay, so if there is no other question, please remind that we have another lecture this afternoon at 3 o'clock. So thank you.
Thank you.